Hi.
Yeah, so I'll try and keep this brief as an additional talk. So what I'm going to present is our development of a new platform for engineering light-matter interaction, the hyperbolic metasurface. This work was done in the groups of Han Kun Park in collaboration with Misha Lukin. Just a brief outline. First, I'll introduce exactly what a hyperbolic metasurface is. Then I'll go into some detail about how we actually realize these structures. And then I'll discuss experimental observations and then give some outlook for what we want to do going forward. So first, you might ask, why would you want to work with plasmonics? Well, plasmonics give you the distinct opportunity to control the flow of light at a deep subwavelength scale. As a corollary to this, you can actually realize efficient light-matter interaction without resonant structures. Of course, plasmonic systems inherently introduce loss, and in many cases these losses are so large that they sort of outweigh these advantages, particularly for the experiments that are discussed in this conference. However, what I'd like to communicate today is that if you, with careful device design, attention to your materials and fabrication, you can actually design devices where the losses are dramatically reduced, and you can in fact realize efficient plasmonic systems. So I'll be talking about a metamaterial today. So briefly, a metamaterial is based on an artificial unit cell with the goal of realizing some functionality beyond the natural realm of materials. So for instance, it was shown famously that a metamaterial composed of copper wire and a split ring resonator, and split ring resonators can exhibit negative index of refraction. As a fun extension of this, the researchers then demonstrated that you could use a similar geometry to realize an optical cloak. So these days, these metamaterials are no longer just limited to, for instance, optical systems. They're also used to engineer acoustic systems. For instance, in this demonstration of an acoustic hyperlens, where researchers showed that with a metamaterial composed of brass fins on a brass substrate, they could spatially resolve sources of sound that are actually closer together than the diffraction limit of sound. So what I'm going to be talking about today is a hyperbolic metamaterial. In these metamaterials, one component of the dielectric function has opposite sign from the other components. And what that leads to, when you solve the equation that relates the dielectric function with frequency in the wave vector, is that you get these hyperbolic equifrequency contours. In practice, these systems are typically realized as a highly anisotropic system, such as a metal dielectric stack or a tightly packed array of metal wires. These hyperbolic metamaterials exhibit a variety of interesting optical phenomena. For instance, they exhibit negative refraction. They exhibit diffraction-free propagation, which can be utilized to resolve sub-diffraction limited structures in the far field. They also exhibit a frequency-dependent enhancement in the photonic density of states. And furthermore, and which is relevant to many, which has been discussed in detail in many of the talks at this conference, they also exhibit these sort of tightly confined chiral fields. So in total, you could see these as potentially useful for quantum optics studies or light-matter interaction studies. For instance, you could take your emitter and place it in proximity to one of these metamaterials, get some enhanced emission from it, and then route the emission with diffraction-free propagation to, for instance, another emitter. And then you could use these spin properties to add another tool to how you control the flow of light. However, these metamaterials tend to share a same common, very debilitating problem, which is that they exhibit extreme propagation losses. So in these systems, the light typically propagates through a metal dielectric stack or something similar, and as a result, the light suffers enormous losses. In the visible frequency regime, you only realize propagation lengths on the order of 100 nanometers. So essentially, you lose all your light immediately in these systems. However, it was recently suggested that there could be a relatively simple solution to this problem of extreme losses. It was suggested that indeed you could realize hyperbolic dispersion and similar properties in a two-dimensional metasurface that's simply an array, that's simply a metal air grating where the pitch of the grating is well below the wavelength that you're exploring. In this system, rather than having light flow through metal, the optical modes of the system are surface plasmon polaritons, which flow along the metal dielectric interface. So based on this suggestion, these metasurfaces were simulated in detail, and indeed it was shown that in these systems you could realize hyperbolic dispersion, you can realize this diffraction-free propagation, you can realize negative refraction. So essentially all of these phenomena that were observed in bulk hyperbolic metamaterials. However, you can observe these properties with a predicted 2 to 3 orders of magnitude improvement in the propagation length, since these waves are flowing along the surface. Furthermore, since you're now in a two-dimensional geometry, this can actually simplify integration with other optical elements. So it's kind of exhibits rich phenomena in a very simple and efficient system. So now I'm going to talk about how we actually experimentally realize these metasurfaces. So in the visible frequency regime, if you want to build an efficient plasmonic device, you essentially have to use silver. So silver has by far the lowest optical losses. However, silver can be notoriously difficult to work with and fabricate. So for starters, if you just try and thermally deposit silver on, for instance, an oxide surface, what you're going to get is a very rough, coarse silver surface. These grain boundaries and roughness all cause losses in fabrication imperfections and are detrimental to device performance. Furthermore, these surfaces are not thermally stable, so you can't do any sort of lithographic fabrication on these, where you'll get coarsening of the grains and the surface will effectively flow around. So what people usually do is they'll take one of these polycrystalline films and do focused ion beam milling, but fib milling can inevitably introduce its own problems, such as defect implantation or increased roughness. So what we decided was that we need better silver to work with. So it turns out that under certain conditions, deposition conditions on certain substrates, you can actually epitaxially grow silver. So what we did was develop a method to grow micron thick single crystal silver films on 111 silicon. This is a typical AFM scan of one of these films. You can see that the surface is ultra smooth. We in fact get roughnesses as low as 300 picometers, and there are no grain boundaries in the surface. So essentially it's as high a quality of a silver substrate as you can get. And indeed, when we do ellipsometric measurements on these films, for instance, to probe the loss in the films, we observe that these single crystal sputtered films have significantly lower losses than, for instance, a polycrystalline film. And then if you take this and simply convert it into a propagation length, for instance, flat silver, what you see is that with these films you can expect, in the visible frequency regime, propagation lengths on the order of 150 to 200 microns. So another nice property of these films is that they're thermally stable, which now allows clean room style fabrication of them. So to pattern these metasurfaces, what we do is that we define alumina etch masks on the surface of the silver, and then we simply do top-down argon etching to actually pattern the silver itself. And this is what the finished structures look like after we remove the alumina mask. You can see that we get these essentially defect-free metasurfaces with high aspect ratio etching. Okay. So now I'll talk about the actual optical behavior of these metasurfaces. So how do you know that you have, for instance, hyperbolic dispersion? So first, let's just talk again about what you expect in these metasurfaces. So at longer wavelengths, where the plasmons are less tightly confined to the surface, they effectively see this grating as a perturbation, which has the effect of distorting from sort of an isotropic equifrequency contour into an elliptical equifrequency contour. As you continue lowering the wavelength, the plasmons become more and more tightly confined to the surface of the silver. And eventually, rather than seeing the bulk silver, they begin to see the grating as an array of nanowires. So arrays of nanowires exhibit hyperbolic dispersion. So as you go to low wavelengths, you'll see this hyperbolic dispersion. And at an intermediate wavelength between these regimes, you'll see this regime of flat dispersion, which is also interesting because in this regime, all of the light propagates in the same direction. Okay, so how do we actually show that we have hyperbolic dispersion? Well, if you look at the group velocity in this hyperbolic regime, you'll see that it's oriented in the opposite direction from the phase velocity along the x-axis. So if we bring a wave in with, for instance, positive kx propagating to the right, and it's in this hyperbolic regime, when it enters the metasurface, its group velocity will switch directions along the x-axis. So it'll appear to negatively refract. So in fact, we do these measurements where we launch plasmons into the metasurface. The metasurface is this region indicated by the white rectangle here. What we see is that in the longer wavelengths, in the elliptical frequency regime, we observe that there is some refraction when the plasmons enter the surface, but not negative refraction. As we continue decreasing the wavelength, eventually we enter this regime where no matter what angle we inject plasmons into the metasurface, they always propagate perpendicular to the gradient. And then finally, if we continue decreasing the wavelength, we enter this elliptical or hyperbolic regime where now we in fact see negative refraction of the waves as they enter the metasurface. So this is just a sort of direct confirmation that we've achieved the sort of dispersion that we were hoping to. So, that's all well and good, but, the main point of going to 2 dimensions was to actually show that we can greatly improve the efficiency of these hyperbolic metamaterials. So to measure the efficiency, I actually just directly measure the propagation length. We launch plasmons into metasurfaces of various lengths and then just measure the intensity at identical outputs. What we measure is that although there is some reduction from the simulated value, which is this black line, which would be essentially a perfect surface with no fabrication defects at all, we still observe that we only get a decrease of about 15 to 40% from this perfect system. So this is nice because these plasmons are tightly confined to the surface, and as a result, they're extremely sensitive to any defects that may be there. And indeed, in this hyperbolic regime, we observe up to 16 microns propagation length, which is a couple orders of magnitude greater than that previous, 100 nanometers that people saw. So I'm not going to go into detail on this, but as I mentioned, there's also this frequency regime where you observe diffraction-free propagation, and we show that we can use this property to resolve in the far field features on the metasurface that have sub-diffraction limited spacing with each other. Okay, so for the last part of the talk, I'm going to discuss chiral effects in these metasurfaces. So generally, this chirality has become quite a popular topic, as can be seen in many of the talks in this conference. Essentially, when you have tightly confined fields, they can develop large longitudinal components. These longitudinal components will be 90 degrees out of phase with, for instance, an in-plane component. So what you'll get is an electric field rotation that's linked with the wave vector k. And this is quite easy to visualize in a plasmonic field. If you just look at it as it propagates across the surface, you'll see that it is indeed essentially rotating. And so there have been many talks about actual experimental realizations of this, some very beautiful works at this conference or at this workshop. There's the work showing that using this effect in nanofibers, you can get, for instance, unidirectional emission. Now they've even extended this to ensembles to create things such as optical diodes, and it's a very cool demonstration. Also, what was demonstrated here and talked about in this conference was that in a solid state system, they were able to get unidirectional emission in these slow light waveguides. And as I mentioned in the beginning of the talk, in these hyperbolic metamaterials, you can also get these same sort of directional effects, emission effects from circularly polarized dipoles. So we are also working in a system with these tightly confined modes. So it's worth asking, how will these effects manifest themselves in our system, which has such strong dispersion with these, in fact, 3 sort of separate frequency regimes. So to probe these effects, what we did is essentially build a test device where we have an incoupling hole etched into the silver, which is essentially in near field proximity to a metasurface. It acts as a dipole source for surface plasmons. They propagate through the surface, and then they scatter off of an outcoupling array, which transmits in-plane circular polarization with some fidelity into far-field circular polarization. And what I should be specific about here is that unlike the talks with the fiber waveguides, the circular polarization I'm referring to is actually perpendicular to the plane of propagation rather than parallel to the plane of propagation. So this is what typical experimental data looks like. This is our in-coupling laser spot. And then at the outcoupling, we typically observe these lobes of plasmons scattering out of the outcoupling. These two distinct emission spots are characteristic of the shape of the equifrequency contours, which have these preferential angles for propagation. And then, so if we just focus on what's coming out of the outcoupling, if we change the wavelength of our excitation, what we observe in the outcoupling is this X pattern. What this reflects is, in a different way from the refraction, but it is reflecting the same thing, is this crossover from elliptical to hyperbolic dispersion. And then if we take this X pattern and then we resolve it into sigma plus and sigma minus components, what we observe is that, in fact, there is this quite prominent plasmonic sort of quote-unquote spin Hall effect in this metasurface. In this system, what it appears is that plasmons propagating, for instance, in the leftward direction in the elliptical regime take on a sigma plus polarization, whereas plasmons propagating in the right-hand direction take on a sigma minus polarization. But what's sort of unique to our system is that we have this very dispersive, these very dispersive equifrequency contours. So simply by changing our frequency, we can effectively flip the sign of this plasmonic spin Hall effect, whereas now in the hyperbolic regime, plasmons propagating to the right now have sigma plus emission, and plasmons have sigma plus characteristic, and plasmons propagating to the left have sigma minus polarization. So what's going on here? Well, for starters, we do sort of fully reproduce this effect in FDTD simulations. So essentially what's happening here, and similar to other systems, you have a rotation of the electric field that's linked to K. So for instance, a surface plasmon with positive Kx will have some electric field rotation of Ex plus IEz. But now in our system, the group velocity is effectively unlocked from this phase velocity. So now plasmons with essentially similar phase velocity can either propagate to the right or propagate to the left. And this is what leads to this dispersive spin Hall effect. Okay, so that I'll just briefly give an outlook of, for instance, what we'd like to do going forward. Again, as has been discussed frequently in this conference, these you can actually have very interesting physics and device possibilities if you have these chiral systems where you have a chiral emitter coupled to a chiral waveguide. For instance, you could potentially observe some exotic physics such as dissipative quantum magnetism or quantum spin dimers. And then this effect can also be the basis for non-reciprocal quantum optical devices. So we also have a system, again, with these tightly confined surface plasmon modes. And similar to these fiber systems, we can also get essentially unidirectional emission from emitters. Well, from FDTD simulations suggests that we can indeed get up to 95% unidirectional emitters from emitters placed in proximity to a metasurface. And what's nice about this system is that since we're operating with small mode volume plasmons combined with some enhanced photonic density of states that comes from the actual metasurface, we can actually get relatively efficient coupling of the emitter with the metasurface, even in the absence of a resonator. For instance, based on these simulations, we can get a ratio of emission into these surface plasmons versus far field emission on the order of 5. So it could be a very nice platform for studying these chiral effects to complement these other systems where they're studying. Okay. So with that, I'll just conclude. We fabricated these metasurfaces into single crystal silver we developed a nice technique where we can do all this with conventional lithography and etching. We observed negative refraction, diffraction-free propagation, this dispersive spin Hall effect, and we observed that all of this can happen with greatly improved efficiency compared to bulk metamaterials. So briefly, I'd just like to acknowledge some people. So this work was done in equal collaboration with Robert Devlin. Also, I'd like to acknowledge Alan Debos, Mark Polkin, and Natalie DeLeon for help with the design and fabrication in those aspects of the work. I'd like to acknowledge Dominique Wild and Janos Purcell from the Lucan Group, who helped work on a theoretical description of this system and helped us actually understand the properties. I'd like to acknowledge our collaborator, Misha Lucan, and my advisor, Hong Kun Park. And thank you for your attention.
All right, thank you very much. Questions?
Yes.
Yeah, thanks a lot for the impressive. Is there in picture what determines what the directionality? So if you want to optimize things like that, so how much is left and to the right?
Sure. Yeah, so we don't have like a full description of the system. So essentially what I've been doing is running FDT simulations in different geometries, and so it would be useful to actually develop a more analytical picture where we understand how to maximize these effects. So yeah, at the moment this 95% is essentially the maximum of what we've simulated, I would say. So.
Generally, right, the more kind of, sort of, the more sub-wavelength, the more, the more kind of into a metasurface regime you go, right, the better.
Yeah, yeah.
Right, more kind of pronounced.
Yeah, so for instance, the coupling, so these simulations are for a metasurface with 150 nanometer pitch. If we can so all of these coupling effects, all of these advantages from having this hyperbolic dispersion are related to how small of a device we can actually fabricate. So if we can move into, for instance, something with half the pitch of this, then we can, for instance, expect this value to double. I don't know specifically how that relates to these chirality effects, though.
But this chirality also goes, I think, it's basically kind of proportional to 10 of the right? So basically you can use this hyperbolic.
Yes. Yeah, yes, exactly. Yeah. So.
People are hungry. All right, so let's thank Alex once again.